Hello guys, welcome to Ramta Solutions. Welcome to your grade 12 Physical Sciences exam prep on optical phenomena and the properties of matter. Today, the question paper we are looking at is the Department of Basic Education's November 2024 Physical Sciences Paper 1. So, because this is an examination, it's important that you read all the instructions. Remember, all the instructions are important. However, I'm going to read just a few. And they are 1. Instruction 8. Show all formulas and substitutions in all calculations. Instruction 9. Round off your final numerical answers to a minimum of 2 decimal places. So in the middle of your calculations, if you have decimal places, work with about 4 or 5 decimal places, and only your final numerical answers may be 2 decimal places. Instruction 10. Give brief motivations, discussions, etc. where required. So this is physical sciences. Unlike business studies or life sciences, it doesn't have essay questions, right? And even history. So this one doesn't have essay questions. So try to have brief motivations and discussions. And advice is that use point forms. 1.1 mark. Okay? Instruction 11. In case you forget your formulas and constants, you're advised to use the attached data sheets. And lastly, even though you are looking for distinctions, it's also important that you improve your handwriting. Therefore, instruction 12. Write neatly and legibly. Now let's get to the work. Remember, guys, this question, or rather this topic, is examined on question 10. Right. It's examined on question 10. So let's see. Now, question 10, let's see. 10.1. By the way, it is how many marks? Let's see. How many marks is this? It is 15 marks, guys. So 15 marks, we should spend 15 minutes. So this video must be over in the 18th minute. Right, let's go. Question 1. Define the term photoelectric effect. It is the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on that metal surface. But I'm going to write it. Process whereby, oh boy. So it's a process whereby electrons are ejected from a metal surface, right? From a metal surface when light of a suitable frequency is incident on that surface. When light of a suitable frequency is incident on that metal surface, right? Okay, so this is photoelectric effect. Proceeding. 10.2. Red light, blue light, and green light are shown simultaneously on a sheet of potassium. So it seems potassium is your metal surface. The potassium sheet is your metal surface. So each color of light consists of a single frequency. Okay. 2 maximum kinetic energies of the ejected electrons are possible, namely 6.96 times 10 to the negative 20 joules and 2.65 times 10 to the negative 20 joules. Each ejected electron has only one of these maximum kinetic energies. Before I proceed, I need to remind you guys, let's say I'm gonna write continuous spectrum of white light. It has these colors: RGB, red, orange, yellow, green, blue, indigo, violet. So what is happening? As you move from indigo to violet, wavelength increases. What does it mean? It means it means also frequency decreases. Remember, frequency is indirectly proportional to wavelength. All right? So we can say now as you move from violet to red, wavelength increases, but frequency decreases. Okay, so this is one mnemonic you should always have. Now, 10.2, let's now see. 10.1, is it? Oh, 10.2.1. 10.2.1. Which color of light is responsible for ejecting electrons that have a maximum kinetic energy equal to 2,65 times 10 to the negative 20 joules? This must be, as you can see, it is the lowest. Red, we have three colors: red, green, and blue. Red cannot be, as I see, these are almost closer, so red cannot be, so I will take this to be green. All right, and then I'm happy that this question is asking you, why are you saying green? So I'm saying green because red light cannot eject electrons. Okay, red light cannot eject electrons. Why? It has a very low frequency. Okay, a red light cannot eject electrons. And then, so red light cannot eject electrons. And again, the reason I'm choosing green is because the frequency of green light, I'm going to write green like this, is less than the frequency of blue light. So, if you recall from your formula, guys, you said energy of a photon is equal to work function plus maximum kinetic energy, right? So if you look at it, energy of a photon minus work function is equal to maximum kinetic energy. So if the frequency gets higher, the difference will be bigger, right? Hence, what does it mean? It means the electrons of the green light will have a lower kinetic energy. Okay, because the frequency of the blue light is higher, it means the EK max will be higher. Right? Great. Now, let's see. Remember, guys, we need to be done in 18 minutes. So we are acting like we are in an exam. Right? Good. 10.2.3. The electrons with a maximum kinetic of 2,65 times 10 to the negative 20 are ejected by light that has a frequency of, do you see this now? The frequency here is 8, this is not threshold frequency, is frequency of the incident light. It is 5,85 times 10 to the 14 hertz. Calculate the frequency of light that ejected electrons with a maximum kinetic of whatever. So now, this is a two-part question. All right, this is a two-part question. So the first part, we said for the green light, which had the 2,65. Okay, so I will say for the green light, it seems we will be looking for work function. We know that, maybe let me not say green light as yet, so I don't have to repeat this formula. I will just say energy is equal to work function plus maximum kinetic energy. All right, now I'm gonna look at the green light. Right, I'm gonna look at the green light. So for the green light, we have HF equals work function plus EK max, right? Let me also add that. So we will say, since I wrote this HF, we can therefore say, remember Planck's constant is 6,63 times 10 to the negative 34. What is the frequency? The incident light here is 5,85. It's 5,85 times 10 to the 14 hertz. We don't know what the work function is, but we know the kinetic energy for green light. What was it? 2,65 times 10 to the negative 20, isn't it? So let's see. 6,63 times 10 to the negative 34 multiplied by 5.85 times 10 to the 14, right? So if you like, you can say this is 3,87855 times 10 to the negative 19 equals work function plus 2,65 times 10 to the negative 20. So the 3,87855 times 10 to the negative 19 minus the kinetic energy 2,65 times 10 to the negative 20. What do we get? We get the work function being, the work function is 3,61355 times 10 to the negative 19 joules. Okay? I am aware I didn't write this to 2 decimal places because we are not done. Now we are going to the red light. Hence, this question is 5 marks. We are going to the red light. Now, again, what do we say with the red light? They said we must calculate the frequency of light that ejected these electrons that brought us this kinetic energy. So we have the frequency unknown. All right, we have the frequency unknown. So let's see. What do we say? We'll say this is 6,63. Remember, guys, this is coming from this equation. Okay, so 6,63 times 10 times 10 to the negative 34. All right, frequencies unknown. What is the work function? 3,635 times 10 to the negative 19. And what was the kinetic energy? It was 6.96 times 10 to the negative 20. Now let's see. I still have this value displaying on my calculator. So I'll just say answer, which is basically saying plus 6,96 times 10 to the power negative 20. Again, this is 6,63 times 10 to the negative 34. Frequency equals 4,30955 times 10 to the negative 19. Now what do? I divide this value here by Planck's constant divided by 6,63 times 10 to the negative 34. So what are we getting? We're getting this frequency to be 6.50 times 10 to the power 14 hertz. This is the frequency of light that ejected electrons with a kinetic energy of 6.96 times 10 to the negative 20. Remember, the work function that I used here is the very same work function I used for green light, because the metal that this light was shown on is the same metal. Okay, perfect. Proceeding 10.2.4. 10.2.4. The intensity of the red light is increased, while the intensities of the blue light and the green light remains the same. What effect will this change have on the rate at which electrons are emitted? So guys, here we are talking of increasing intensity and the number of photons, and we are increasing intensity of the red light. Remember, when increasing intensity, we are not increasing frequency. So increasing intensity does not, especially for red light on its own did not eject electrons. So this therefore means there's nothing that will happen. So our answer will be remains the same. Okay, remains the same. Why? Because this frequency does not emit electrons. Okay, perfect. Now 10.3, interesting part. Let's hear. Some of the atoms of a hot gas, interesting. Some of the atoms of a hot gas made up of a single element are in an excited state. The spectrum formed by a hot gas is observed on a screen in a darkened room. Darkened room. Guys, when we say darkened room, you should be having an idea that somehow darkened. Remember our spectrum. When we talk of a darkened room, that means what will be happening here? There will be colored lines that are appearing on a dark screen, and that should be saying to you, you are expecting an emission spectrum. So let's see. The spectrum formed by a hot gas is observed on a screen in a darkened room. The spectrum consists of specific colored lines on a black background. Oh, interesting. 10.3.1. Name the type of spectrum formed. It is the emission spectrum, or if you like, you can say line emission spectrum. Okay? It is emission spectrum. Okay? It is the emission spectrum. Okay? That's 10.3.1. Now 10.3.2, explain the presence of the colored lines in the spectrum. So these, what do they mean? These colored lines, what they mean, they represent, let me just say this, the colored lines represent frequencies. Colored lines represent frequencies of ejected electrons, right? Yeah, frequencies of ejected okay, no, not to say ejected, represents frequencies of photons, better that way, represents frequencies of photons when electrons are emitted, should I say from a region of higher concentration? No, when electrons are emitted to a lower energy level. Yeah, let me just save space. This is an exam and save time as well. So what I would have loved, I would have also said the colored lines represent frequencies of photons when electrons are emitted from a region of higher energy level to a region of lower energy level. But it's also easier to say when electrons are emitted to a lower energy level. Okay, when electrons are emitted to a lower energy level. Okay, and this is it, guys. This is how you attempt this question. So, bye bye.